Thanks, Bernard. Welcome. So we're just talking about PS3 briefly before we start. I mean, the short answer is that it's just like remember the calculator thing you did for me, with the little math.h or whatever, math.c with your add and subtract and so on. It's exactly the same thing. Like those functions, add, subtract, and all of those. Once you included that header file into main, now main has access to all those functions. It's just as if you plopped math.c right in that spot in your file, so you can see all of those things. It's just the same in like the node and the list and so on. All of your list functions go into list.c and get mapped into list.h for their headers. Once you include list.h, now you have access to all of those functions in main. So you can call and all the variables as well that are in list.c. So it's not like an object where I've got to create an object and then instantiate the object and then talk to it. Here it really is just I got a bunch of functions that are available to me and defined in list file. Like list keeps track of head. You don't have to keep track of it. List does it for you. When you pass that first node in, if head is null, and it just populates head, and then that persists through the entire run of the program. And that's why we can fully form a node and then hand that node via a pointer, just hand it over to the list. And the list knows what to do with that node to put it in the list. And like the idea is that we're to, and I use the term on Piazza as well, it's a separation of concern sort of thing. I want list to more or less be isolated from node. I mean, it's C, so like we would have to take great pains to totally isolate those two things just because it's so easy to get into a node and see what its values are. Like really, if we wanted to do it right, node would be completely transparent to list and would offer an interface. Like, oh, you want to sort the node? Well, node would have an interface, sort, nodes or something, and that would be a pointer to a function that would get called to sort the list. Like that's way too much work for the kind of time we have. And so there's always going to be this little gray area where list kind of knows a little bit about node knows a little bit about the list, less so than list knowing about node. Like list, for example, has to manipulate pointers inside the node, so it knows how to get to those pointers. But for the most part, they really are kind of separate. So list does list operations. It can count the nodes. It can sort itself. It can print itself. That's why it's a void signature for print list. It's really a function on list, and all it does is start at head and print the value of each node going down, until the bottom. It doesn't need to know head. List already knows head. Especially if you come from Java and Python and so on, working in objects, like it can be a really awkward transition because there just aren't any objects. It's just code. And just remember that the include essentially plops the code that you're including into that spot in your file. And so you have access to everything that was in there. At some point, list.c gets compiled and then linked in. So you have access to all of those functions and variables. And frankly, there's nothing to say that I would mark you down if you did, but like, node could keep track of head and say, hey, put this node at the head of the list or something. That would work. Like that would work fine because you have access to all the variables, but it would break that separation of concern that I want list really to do list stuff as much as possible and node to do node things, and not really, except in those edge cases where we have to do it, like really not know much about each other. So that's kind of where I was going with PS3, and I encourage everybody to ask questions about that because it can be an awkward transition into this language from another language. We're used to doing things a certain way. We used to do them slightly differently in C. And to be honest, like I'm an object-oriented guy, so like I'm mainly writing code in C++ or TypeScript or something where I have objects, and so I have the same issue. It's like, it's easy to do with objects to separate those things. It's not so easy in C. And so I have to think about it when I'm writing that code. It's like, how am I going to do that? Anyway, all that to say, ask questions about PS3. Ask tons of questions because that's how we all learn it, right? All right, cool. So Today, class, we're going to kind of take a step back from C a little bit and start to look at things more on the systems side, because it's a systems course, not a C course. Yeah, like a C course. Like we'll bounce back and forth kind of as we go. So for example, last week we were just doing mallocs out the wazoo, right? Oh, malloc this, malloc that. And I kept saying, oh, it comes off the heap, comes off the heap. And I mentioned the stack or something. It's like, well, let's flip now and look from the process side, the system side. What is the heap? Like, where is the heap? How is it managed? And that sort of thing. And we'll do that as we go forward. Like we'll talk, in like 2 or 3 lectures, we'll talk about the stack and how we use the stack to do function calls and so on, and how the stack grows and shrinks, what a stack frame looks like from the system side. And then we'll go over to the C side and implement some stack functions so we understand like how does a stack really work? How would I code it? And like you see both angles from it. I mean, this is not an operating systems course. And so like we're not going into a lot of gnarly detail on the OS side, but it's almost like in the operating systems course, like 350 or 550 or something, you're taking a look at processes from the operating system standpoint. We're doing the opposite. We're looking at the operating system from the processes standpoint. And the process means that it's, a process is a program, essentially, maps to a program. And I'll probably start using the word process instead of program. Process. Because that's really what we call them. And I've been calling them kind of both up to this point. But now like we're more mature, right? So I can talk about processes instead. So that's kind of the map for what's going forward. I'll remind you on Thursday, but next week we have a day off. We have that day of rest or whatever the heck they're calling it that replaces spring break. Like it actually replaces spring break. All right, cool. People were really, like, A1 was really into this lecture. I don't know why. Like a bunch of the stuff in the front, like it was just sort of historical background and stuff. There are tons of questions. Like, okay, that's what you want to talk about. We'll talk about that. Will I be having class on April 20th? How am I supposed to? What is April 20th? April 20th, is it like an actual day? Oh, 420. Oh, sweet, sweet. Is it a Thursday or a Tuesday or something? We're gonna have to have a celebration. Oh, it's a Tuesday. Oh yeah, sure. Yeah, 420 for sure. Although 419 is interesting also. The day before is also a holiday. So 420 is a holiday, of course. 419 is bicycle day. And we all love bicycle day. Bicycle day celebrates the day that that Dr. Hoffman took the first acid hit ever and hopped on his bicycle and rode home and thought he was going to die. So that's 419. All right, let us talk. Let us talk. You guys are already planning 420, huh? You degenerates. All right, programs in memory. 421 National Random Drug Test Day. Yeah, no kidding. No, actually, Jonas, nobody mentioned 420. No, we're talking about computers. All right. If I don't talk about enough about computers, I get yelled at. It happens periodically. I know. All right, so just what I said. We're talking like we're in the process looking out at the operating system to see how stuff is managed for us. And we do a little bit of operating system stuff, but it's not an OS course. But like, Thursday we'll be looking at the heap, specifically at the heap, and we'll look at, because the heap is inside the process. And so it's kind of fair to see how that memory is managed. Like, how do we allocate a block of memory out of the heap? How do we, when something's freed back to the heap, like there's a lot of stuff that has to happen at that point, like coalescing memory blocks and so on. So we'll talk about that. But again, from the process standpoint, not the OS standpoint. All right, I get to draw today. It rocks. All right, let's talk memory, because maybe we'll be mucking around in memory for this lecture and the next. Like, let's just talk about memory and a little bit of historical perspective. This is what A1 was so into. I think it was a delay tactic. They didn't want to get into the real meat of the stuff. So, oh, let's talk about the 40s. What was it like in the 40s, Professor Donham? Like, yeah, if you, I was not alive in the 40s. I'm a child of the 60s, 1960, almost the 50s. All right, so memory, like the architecture of these computers that we use, they haven't really changed for a really long time. Like even the 40s, where we're looking at like ENIAC and all those like big room-sized machines, they were pretty much laid out the same way as our machines today. Is this working at all? Sort of. This room has great acoustics, thank goodness. It was an old synagogue. Actually, the Torah cabinet is right behind the screen. It's kind of cool. Tell us about the 60s. I don't remember much of the 60s. So the architecture really hasn't changed much. Like, if you think about it, it kind of makes sense, right? Because I guess there are ways to build machines that are different than what we do here or have done for the past 50 years. But like this is the architecture we sort of fell into, and it's just progressed since then. In the past 80 years, since the 40s, like it just keeps getting smaller and faster and cheaper and more efficient. But really, the general architecture is roughly the same. Like in those 40s machines, if we looked at a picture of, I think it was ENIAC, so real quick, bang W, ENIAC. Bang W takes you right to Wikipedia. So here's some pictures of ENIAC, one of the early, this is the grandchild or grandfather of modern computing. It's like you program these things with these jumper, see all the jumper cables everywhere? Those were patch cables. They look like phone patch cables with 1/4-inch plugs on the end of them. That's how you programmed it. And you were essentially connecting relays together, relays and vacuum tube inputs and outputs. And you were configuring a circuit essentially to do a calculation. And in terms of the memory was more or less like that. Well, that's a little awkward, but these are tubes on the backside of the machine. Like between those and the relays, that's how memory was kept. And it was either on or off. The relay was open or closed. The tube was on or off. Like these were driven as switches mainly. So it was essentially a switch, on or off. On or off represents 1 or 0. So these were binary machines. Is there a better picture of that? No, not really. So these were binary machines as they are today. So this architecture, this shape of these machines kind of looks exactly the same on the Mac. It's just a lot smaller. Like, in fact, here they've got, like that picture, ENIAC on a chip. Like that's a chip, the size of your thumbnail basically, that represents everything that machine could do. This enormous, that thing was literally filled a room, and now we can stick it all on a chip. But the architecture is roughly the same. It was really like a decade later in the 50s that John von Neumann came up with kind of the blueprint for digital architecture. I guess that's on the next slide. Oh, let me show you this one. Make this big. So memory in these machines, like past 1940 and more into the 50s, 1950s and forward till like late 60s even, mid to late 60s, memory in these things was, it was magnetic beads like this. So this thing, play, here's my laser. Here's my laser. So this thing here, like these are address and data lines, and it's laid out in a grid so that you basically would activate a set of address lines, and where those address lines intersected, like, and by activate I mean put voltage on. So you put voltage on address lines, and they would intersect at a spot. And that spot, because there was voltage on those wires, it would magnetize this little magnetic bead. If you wanted to, like that would be a 1. If you wanted a 0 there, you'd reverse the polarity of the, and that would demagnetize that bead, or at least make it the opposite polarity. and a 1 or a 0. You either had a magnetic field on that bead or you didn't, 1 or 0, so two different states. The nice thing about these core memory, this is core memory, the nice thing about core memory was that once you'd magnetize the beads, so once you'd loaded up this memory, the magnetism stayed. It wasn't electromagnetic, it was just magnetizing a magnet. And you could pull these things out of the machine and put them on the shelf, which meant that we could load up programs in these, load up our program, pull it out of the computer, and put it up on the shelf till we actually wanted to run that program. And when you run it, you just take the memory card, stick it in. It's just like a thumb drive these days. We're used to that sort of technology, but back then, this was a big deal. Like, these were really, really expensive because they were handmade. These were hand sewn with the wires going through the beads and so on this frame. And this is a really, really tiny one. So it's like, I don't know, a couple hundred bytes of memory probably. Here's von Neumann, just like Dr. Seuss. So John von Neumann worked in Philly at the new Moore School of Engineering, and he was working with, he had a team of researchers there, and they were collaborating with some folks down in Texas. They produced in mid-50s describing what they thought would be like the base architecture for digital computing. That was the purpose of the paper. And they came up with this diagram or something similar to it. It really is like, again, it's the same thing we use today. In our computers, like our Macs and so on, like we have a CPU. That CPU has an arithmetic logic unit in it. It does all the math bits. The control unit controls things like memory access and so on. I've got memory, and then input and output. Oops. Those I/O pieces, back in von Neumann's day, I/O meant input was probably off of paper tape or maybe a teletype keyboard sort of thing. We didn't have monitors or anything, and output was probably a printer or tape or something like that. But really, like, this shape is exactly what we use. Like, it hasn't really changed all that much. We're going to talk specifically about memory. I mean, there's some issues with this, of course. Like, von Neumann's design had everything on a single bus. So memory, math, everything was on one set of wires. And so there was a lot of delay. Like, you wanted to write something to memory, but there was data being sent to the arithmetic logic unit. Like, you had to wait until that was done till you could put your data on the wires. So there were issues around that, but those were really just implementation details, just tweaking the implementation. The overall design is pretty solid. So we're interested in the memory parts of this. Now, in computing, memory looks like a big spreadsheet, like literally. So if you think of a spreadsheet in like Excel or numbers or something, and just one column, so a single column spreadsheet. The first cell is 0, right? So it'd be A0. First cell is 0, next cell down is 1, cell below that is 2, and so on. It's exactly the same with computer memory. Computer memory is laid out as a giant one column spreadsheet. Each of the cells in memory, so in a spreadsheet, we can type whatever we want. Each cell in memory in a computer is 8 bits wide, typically. So 8 bits, 1 byte. So 1 byte of memory, 8 bits, and then just one after the other. We've actually seen that several times in CLion when we look at stuff sitting in memory. Like, each of those little groups of bits, it's 8 bits. In each little group, that's 1 byte of memory. And if you look at the addresses on the left, when we look at stuff in CLion, you'll notice that, there are, 8 of them across, so it goes up in groups of 8. We're looking at 1 byte at a time. I mean, there were some other weird things, like IBM, for example, they had a 6-bit architecture instead of 8 bits, which we kind of, it was an historical thing. Like, they went down a design path pretty early on, like early 50s. They went down as a design path that led them to an architecture with 6-bit bytes and a really oddball instruction set, and the way it was run, it turned out to be really, really fast. So they didn't abandon it. That was their mainframe architecture. But the problem was that the rest of the world sort of moved on from IBM. Like, for example, you remember ASCII? ASCII, we represent characters with a number. like 65 is an A or something. Well, it's a 7-bit code. You have 256 characters that you can use, 0 to 255, 7 bits. 2 to the 7th is 256. Well, unfortunately, IBM only had 6 bits, so they had 2 to the 6th possible characters. 2 to the 6th is 128. Is it? 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So 2 to the 6th is 64. Like, they didn't have a lot of character space, right? 64 characters is not a lot of characters. And then, so like, if you were working on data coming out of an IBM mainframe, it was all on EBCDIC, and you had to translate that into ASCII. It turns out that in A1, it's like, I have no idea what EBCDIC stands for. So we looked it up. It turns out it's extended binary coded decimal something. EBCD. I don't recall what the IC was. Yeah, they were doing weird things in memory, like storing decimals instead of binary and so on. Anyway, for us, what we really care about is, oops, didn't mean to do that. I meant to do this. Move you up a little bit. I was trying to find a nice spot for that. But that's not horrible. So for us, basically, we're starting at 0 in our memory space, and our processes are going to have a 32-bit address space. So 32 bits, in 32 bits, binary digits, I have 2 to the 32nd possible combinations of ones and zeros. So 32 individual ones and zeros. There are 2 to the 32nd combinations of zeros and ones. 2 to the 32nd is roughly 4 gig, 4 billion. So I've got about 4 gig of memory allocated to each process that's running. If I had a 16-bit address space, like 16 address lines, 2 to the 16th is 65,536. So that would be, we call that 64K. There's a, we actually had a much longer discussion than I had anticipated. So just that I said something like 64K, and they assumed that was 64,000. And then they said, well, how does 64,000 map back to 65,536? I had to explain that there are 2 Ks. You probably remember this from some course at some point. In engineering, K is a scientific unit, and it means 1,000, like 1,000. That's what K means. In computing, it means something different. In computing, it means 2 to the 10th. 2 to the 10th is 1024. And so a K in computing is slightly larger than a K in engineering, and that's why 64K is 65,536. It's 64 times 1024, essentially. I assume that comes out something that's relatively close. All right, let's talk briefly about hex, because as I told A1, I'm just not quite sure where you guys are in what you know. I just wanted to level the field to make sure we all know what hex looks like, because this is kind of what we're going to be working on. So it's just a really quick refresher. And if any of this confuses you, you might want to go back and just take a quick look. I think our book probably has a little chapter on numbering systems, including hex. So in hexadecimal, hex is just a numbering system. And it uses, in the case of hex, it uses 16 symbols. So in decimal, for example, counting numbers, 1, 2, 3, 4, 5, and so on, the numbers we're used to using are in decimal. I've got, deca means 10, right? So I've got 10 symbols. I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different symbols. Numbers in decimal are expressed as base 10 numbers. And we'll see what that means in a sec in terms of hex. Octal, for example, octo means 8. So in octal, I've got 8 symbols, 0, 1, 2, 3, 4, 5, 6, 7, and my numbers are expressed in terms of base 8. In binary, how many symbols do I have in binary? 2, right? I get 2 symbols, 1 and 0. And so when I'm expressing binary numbers, I'm working in base 2. So it's always the number of symbols is the base I'm working at. And we'll see why bases are important in a sec. So hex, I'm in hexadecimal. Hex means six, I guess. Decimal means 10, so 10 and 6 is 16. I've got 16 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go with letters. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So 0 through 15, essentially, in 16 symbols, I'm in base 16. You'll see why we'd use hex in just a moment. The short, the TLDR is that hex maps really cleanly onto binary. Like it's really simple to move back and forth between binary and hex. And it's just really hard to remember binary numbers. Like if I have to look at a big string of binary numbers, it's really, I'll probably have to pull a calculator out to tell you what it is. Or if I'm comparing things or doing math, like subtracting and so on, it's just so much easier to do it in hex instead. And because they map so quickly, I can, if I see a binary number, I just pop it into hex almost directly and then work in hex. And then if I need the binary, I can go back to binary pretty quickly. So for example, each digit in hex is 4 bits. It makes sense. I've got 16 characters, 16 symbols, right? 0 through 9, A through F, so 16 things. How many bits do I need to go from 0 to 15? It's really the log base 2 of 16 is the question. It's 4. In 4 bits, everyone's dead, barely. In 4 bits, I can go from 0, 0, 0, 0, which is 0. 1, 1, 1, 1 is 15. And so in just 4 bits, I can represent all 16 of my characters. It just means that every digit in hex maps onto 4 bits of binary. So a 9 in hex maps onto 9 in binary. 9 in binary is 1, 0, 0, 1. 8 plus 1 is 9. And vice versa. If I've got like a 4, or let's say I've got an 11 in binary, that's 8 plus 3, right? So it's 8, 0, it's 1, 0, 1, 1 is 11. 8 plus 2 plus 1, like those 4 bits represent, well, 11 is B in hex. So those 1, 0, 1, 1 represents a B. Here's a nice chart for you. Like that. Well, if I'm talking about memory in modern computers, 1 byte is how many bits? 8 bits. How many hex digits do I need to represent 8 bits? 2 of them, right? So every byte I can represent as the combination of 2 hex values. So in my, how many combinations in 8 bits? It's 2 to the 8th. What's 2 to the 8th? 2 to the 8th is 256. Very good. So 2 to the 8th is 256. So I can actually have values from 0 to 255 in 8 bits. I can represent values from 0 to 255 in 2 hex digits all day long. And just a quick aside, we'll almost always see these numbers in hex written as 0x something. The 0x just means it's hex. It's just a label. 0x means hex. It's just an alert. It's actually not stored in memory as 0x something. That's just for us to recognize that it's a hexadecimal number. Like 11, is 11 binary? It's 1, 1, right? Is it binary? Is it 11? Is it base 10? Is it base 8? Is base 16? Who knows? If you put a 0x in front of it, 0x11 is clearly 17 decimal because it's 1, 1 in hex. Question, oh, thank you, questions. Is DA basically 10 plus 16? It's more like 10 and 16 next to each other. You'll see in a slide coming up, Bernard. Wouldn't base 32 be better? Too many symbols. I think it'd be too many symbols. Like 32 symbols, we'd have, uppercase, lowercase. Like it'd be a mess, I think. I've never actually seen anything more than base 16 in computing. Although really, like Sam, like if you had a computing architecture that had like 20-bit bytes, like your bytes were 20 bits wide, then why not work in like 2 to the 20th or something? I don't know. I mean, in base 20. We wouldn't see that, of course, but it would work. All right, let's convert. I'm trying to speed through this because again, I don't know how much you guys know. Here's where the magic happens. So if I want to convert binary to hex, so I'm looking at a binary value, I want to know what it is in hex, or going the other direction, all you have to do is break it up into 4-bit chunks. So here I've got this big number here. All I've done is to break it into 2 4-bit chunks. If I'm short over here, like on the left side, if I had, this is 8 bits, if I had 7, you just pad with the zeros on the left, because zeros don't mean anything. And by padding, but padding means type it. Padding just means I'm going to add extra zeros to the left to get it to 8 bits or some multiple of 8. But here's my binary value. Just break it into 2 chunks of 4 bits each, and then literally just write down the value of each of those 4 chunks, or each of those 2 chunks in hex. So this one, 0100, 0100 is 4 in binary. So just write 4. This is 8 plus 4 plus 1 is 13. Just write down the hex value for 13 is a D. So 1101, 0100 in hex is D4. And for me, it's just much easier to think about D4 than it is the binary. But going the other direction is easy too. You just reverse the process. So if I'm looking at D4, I want to know what the binary representation is. Take the 4, write 4 in binary, take the D, write D in binary, and I'm done. Either just you'll remember them at some point, or you can refer back to the chart, or just count on your fingers. Don't count on your fingers in an interview. Don't do it. Unless you see the interviewer counting on his fingers or her fingers, then you can follow their lead. Anyone need to know more about this? Like any questions out there about bases and conversions and so on? I went into it in a fair amount of detail in A1, and it may have been too much.
Just one quick question.
Just go ahead.
Some intuition about that, because the way I like to think about it, so the first digit in the hexadecimal, right, is just from 0 to 15, right? So you have 1 times 4, for instance, and then you basically say plus 16 times kind of D, right? And then that's the value you have in the end. It's like 16 times 13, isn't it? So the whole thing evaluates to 212 in decimal.
Oh yeah, I think I see what you're saying. So that full value, like this whole number, this whole number, well, let's figure out what it is. 1101, 0100, 1101, 0100. Okay, so it's 1101, 1101, 0100. Like that, right?
I think so,
yeah. So yeah, I mean, it's one large number. I don't know what the number is, but so we're in base 2, right? Because I've got 2 symbols. So this is going to be the 2 to the zeros column, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. Those are my values across the top. And the way bases work, so I'm in base 2, which means I have 2 symbols. I'm in binary. If I was in decimal, it'd be base 10. So it'd be 10 to the 0, 10 to the first, 10 to the second, and so on. If I was in base 8, octal, 8 to the 0, 8 to the first, 8 squared, and so on for each column. It's like this we can just add up. What's 2 to the 7th? Let's do it this way, I guess. 2 to the 8th is 256, right? So 2 to the 7th is 128. So 2 to the 7th is 128, plus 2 to the 6th is 64, plus no 32s. 2 to the 4th is 16. 2 cubed is 8. 2 to the 2 squared is 4. And that's it. So it's 20, 84, 84. It's 212. So that's 212 decimal. that what you were asking, Jonas?
Like I guess, like it works. This like my question was just it works the same in hexadecimal. So you have 16 to the power of 0 times then the value that you have there, plus 16 to the power of 1 for the second digit in a hexadecimal number, etc., right? I think that was just the question I was asking.
Yeah, maybe.
So the
I'm
same
not sure I'm
like
really hearing.
what we're doing here, right? So for the first digit in a binary number, you have 2 to the power of 0, then times 0
Mhm.
or 1. And if we have a hexadecimal number, like if you go back a slide, I think it was, we
Gotcha.
have, 4 times 16 to the power of 0 plus d, which is, I think, 13, right? Times 16 to the power of 1, etc., etc. And this is how it will continue, right?
Yeah, that's exactly it, Jonas. You
Okay,
got
okay,
it.
okay.
So, yeah. Um, I can't even erase that. That sucks. And let me just do a quick, actually, we'll do a quick one on slide coming up, I think. Well, not really. Uh, yeah, here's one. So here, I think this is your question. So here's 3e6. Like what is that value in decimal, for example? And it looks like that. I'm in base 16. So it's 16 to the 0, 16 to the first, 16 squared in each of the columns. Next one would be 16 cubed. So it is, anything to the 0th power is just 1. So this tells me I've got 6 ones. 6 times 16 to the 0th power. 16 to the first power is 16. So I've got E16s, 14 times 16. I've got 3 16 squared. 16 squared is 256. If I had one to the left, what's 16 cubed? 4096, right? So you just take, and I've got, like here, I've got 3 16 squared. So it's 3 times 256. And then you just add them up like that. So that's 998. If I wanted to express it in binary, how many bits would I need to express this whole thing in binary? Each digit is 4 bits, right? So I got 3 of them, I need 12 bits. And I would just write them down. So I'd write down a 6 in binary, 1100. I'd write down to the left of that, you would write down 14, which is 8 plus 4 plus 2, so it'd be 1110 is 14. And then 3 is 0011. So just write those binary values for the 3, the E, the 6, and that's the 12 bits that gives you 998. 12. Oh, thank you. So truly, I thought there was just like a random number. That was actually 12 bits. All right, cool. Everybody reasonably comfortable with that? Like from our standpoint, at some point, like we'll be doing bit manipulation. So we'll be doing like way down in the weeds, like moving bits around and masking and so on. And we'll bounce back and forth between hex and binary. Just hex just because it's easy to read, and then binary because we'll be working with individual bits. So just make sure that you're comfortable with both hex and binary, at least to read them and have an idea of what the numbers are. I mean, binary is probably where we'll spend most of our time in that kind of exercise. But we use both. Like when we're talking memory, we're almost always talking hex, just because memory is very large numbers. It's just easier to read in hex. All right, sweet. Let's keep going. Let's keep going. So let's talk memory. Here's this is Apple memory. This is an Apple II, mid 70s, late 70s. This was the memory address space for the Apple II. I've got 0 to FFFF. How big is that memory space? So each hex digit is 4 bits, right? And I got 4 of them. So it's 16 bits. So the memory address space is 2 to the 16th. 2 to the 16th is 65,536, which is 64K. So this was a 64K machine. And here's how it was broken up. This bit down in the bottom, lasers, this stuff down at the bottom where it says BIOS, that was all the basic operations of the computer. So for example, the keyboard code would be down there. When you press the key on the keyboard, it generated an interrupt into the CPU, and the CPU would then call a function inside the BIOS to handle the key press. Handling a key press means reading the key code off the keyboard, moving that key value into a buffer somewhere, and then flipping a bit to tell somebody that somebody pressed a key. Booting the machine. How do I boot the machine up? Well, that's all in the BIOS. So the BIOS is ROM, that's read-only memory. That's, burn once, read mostly. You burn this stuff into silicon and it can't change. Now, there's other forms of ROM, like there's uh, EEPROM. EPROMs are erasable PROMs, so I can erase it and then rewrite it. Usually those would use, these ones I worked with way back in the day, use ultraviolet light to erase those memories. And they actually had a little clear window, a crystal window on top of the chip that you could see the memory through. So you would burn the memory in, and to erase it, you held it under a UV lamp for a while, and that would erase the memory. I don't know how it did it physically. I never thought about that. Yeah, Joe, 0x just means hex. Anyway, that's BIOS. And it was popular back in the day. Like the BIOSes, like there were a couple of manufacturers of them. For example, Phoenix was a big manufacturer of BIOSes. AMD came along. Was it AMD? No, it was Award. You might see Award BIOSes. Like each BIOS manufacturer built their own chips, and you could, like, if I had an Award BIOS in my machine, they were usually in a socket. I could take it out of the socket and plop in another BIOS in there and play with that. Or I could write my own BIOS because it was on a removable chip, just write my own or modify the one that was there, burn it to a chip and then drop it in. Like we had great fun back in the day modifying computers that way. But this is it. Like this is all you've got for your entire computer. The Apple II, like this architecture on the Apple II, this was mainly a one-trick pony. You would load a program up and run it. And if you wanted to do something else, you would load another program up and then do something else. There was no multitasking, like there was no concurrent, anything. It was just you load up a machine with a program and run it. And when you're done, you shut it off and maybe load another program. It wasn't very sophisticated. The IO space was mainly drivers for things like printers, the mouse. If you had a mouse, didn't have a mouse on an Apple II in '77. But basically stuff that was input out, a tape device. You were dumping stuff to tape. That's where the code for that IO stuff would go. And then you had the entire remainder, the whole 48K to do whatever you wanted to with. We wrote some really sophisticated programs that fit into 48K. So it was not an insignificant amount of memory, although we always wanted more, of course. And then we kind of moved on to, like, from there, really it was early 80s that IBM started working on the IBM PC. And that kind of changed everything. Like the IBM PC, their big thing was, oh, holy crow, now I've got a 20-bit address space. What's 2 to the 20th? A gig, right? Or I'm sorry, a meg. So 2 to the 20th is a million-ish. So this is a megabyte of memory. 64K, like that's a huge jump in the size of addressable space. That is not to say that you could buy an IBM PC in 1984 with a mega memory in it. I suppose you could if you were like a nation state, because they were really expensive, like crazy expensive. So most of us got the 8K version, or I remember I had a 4K version that I upgraded to 8K at great expense. Like memory was on short supply. One cool thing we did though, like even with that limited amount of memory, if I had only 16K memory or 8 or something in my machine, I could still write really large programs. We used overlays for those. So the technique was you would read the first part of the program into memory where it started to run. Mainly these were sequential programs. So we get down to a point in the program toward the bottom of memory. There would be an instruction to load the next part of the program from tape. So you'd run your program till essentially you're running out of memory. Then you'd load the next part of the program into memory. It would overwrite what was already there, and you'd jump back to the top and start running from there. Then at the bottom, you have another load instruction to load the next part on tape. So you could really have unlimited size of program but it kept having to load pieces of it from tape because memory was so small. What else is interesting about this? Oh, this part was interesting. So this video RAM piece here in the blue, that was implemented as, so each bit, or I'm sorry, this is a IBM PC, it's IBM PC in 84. Each byte mapped to an individual pixel on the display screen. And there were two chunks of it. So imagine like a 640 by 480 screen, all mapped directly. So every single pixel mapped into a byte of memory. If I wanted to show something on the screen, I would just move a value into memory in that location and it would show up on the screen. Same thing with the printers, like on this architecture. It doesn't work anymore. On this architecture, like that IO piece, if I had a printer attached there, the printer mapped directly into memory. So if I wanted to print something on the printer, I would move the ASCII value in location in memory in blue. And because it was mapped directly to the printer, it would then appear on the printer as well. So they sort of shared a view. The computer had a view of that piece of memory. The printer saw the memory too. And that way I could print stuff on the printer. Same thing here, that video RAM, there were two buffers, two 64K buffers. And so you would be displaying the first buffer, the 64K on the screen. While you were displaying it, you'd be writing the second buffer. And then once the second buffer was ready, you'd flip them. So now I'm displaying the second buffer and writing into the first one. And he's kept doing this, back and forth, writing one chunk while you're displaying the other. It allowed you to, I mean, with the persistence on those screens, you could get some pretty smooth animation, even if, these machines are running at like a megahertz or so, like really, really slow machines. But because of this buffer swapping, you could get some pretty clean animations, even on a slow computer. How big was this IBM computer? Like physically, the original ones were like pizza box size and a little bit bigger. And then of course they started licensing out the architecture to other manufacturers. And that's when we started seeing the desktop towers and so on. So they were physically roughly the same size as a tower that you would have these days, but much simpler. Like these machines, I could pull out a soldering iron and some snips and start working on the guts. And we used to do it all the time. Like, oh, I want to increase the clock speed. Well, I'll just go in and find the clock circuit on the motherboard, and there was usually a divider in there somewhere, and so I just replace it with my own divider to increase the clock speed. Soldering iron and some snips, and off you go. Those were the days, I tell you. Actually, was it around this time, 84-ish? Yeah, it's probably around this very time. So I was, at this point in my career, I was the technical editor of Insider Magazine, which was a magazine for Apple enthusiasts. This is around the Apple IIc timeframe. And one of my jobs was to write technical articles on how to modify the computers. So, you want to add a modem to it? Yeah, sure, we can do that. Whip out your soldering iron and follow along. And we just get down to the guts of the hardware and play with stuff in the hardware. Those are great days. All right. So let's talk about the modern view of memory, like the stuff that we're going to be seeing and talking about in here. Oh, there's a couple of concepts. Like we'll talk about the processes view of memory for the next lecture or so. The processes view typically is 32 bits. So each running program essentially gets 32 bits of memory. So 2 to the 32nd is 4 gig. Every running program, every process sees 4 gig of memory space. Well, I mean, that's already we're in trouble, right? Because man, get out of this. Escape. X. Thank you. We're already in trouble because, like, let's just pop over an activity monitor here. I think it's a task manager on a Windows box. Like, how many processes do I have running on this machine? I've got 541 processes running. Each of them see 4 gig. So if you multiply 4 gigabytes by 540, you get a really freaking large number, really, really large. Like how much memory do I have in the machine? I've got about the smack, I've got 8 gig of RAM sitting in there. So I have 8 gigabytes of memory, enough for 2 processes, but I have 500 something processes running and they each get 4 gig. Like, how does that work? Well, it's called virtual memory, and we'll talk about it probably starting next week. We'll look at some virtual memory stuff. But from the process standpoint, like from our view, looking out of the process into the OS, from our view, the process gets 4 gig of clean space to work with. Every single process does. We'll see, coming up in a lecture soon, how that maps onto physical memory in the computer. I think there's one slide in here that kind of shows it, but not really. The cheap way is to split it in half. And splitting in half is like, that's my internet unstable, and it's not the only thing unstable here. Hey, Piazza, you guys still hearing me? You see me? Piazza. My guy's out in Zoom space. Can you still see me? Did I lose him?
We're still here. Hello, hello.
Okay, good. I was getting alerts about network here. I lost the chat. That's what's going on. Where's my chat? Hang on. More chat. There you are. Yes. Nice. All right, so each process gets 4 gig. And the address spaces run from 0, like, 0 is the first memory address, 1 is the second memory address, and so on, all the way up to FFFF, which is 4,294,967,295. So it's 4 gig of space. If I wanted to split this directly in half, there's a really cheap and simple way to see which half I'm talking about. And the reason we split it is the operating system needs some stuff in that space. And then the program itself needs some stuff, and they don't really mix. So if I'm trying to use things that are the operating systems things, they're going to be in one piece of this memory. My program stuff is going to be the other piece. They can't really cross each other. If you do try to access something in the operating system space, that's a segment fault. You're not assigned to that segment of memory, and so that'll crash your program. But the cheap way is just to look at the last bit, like this. If I had, throw it in here. So let's say I had a 4-bit space, right? 2 to the 4th is 16, so I have 16 memory locations. Well, in 4 bits, it goes from like 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1. How do I divide that into 2? Just divide it in half. It's really the last bit, right? So if I get to here, that's 7. What's the next value up? The next value is going to be 1, 0, 0, 0. I'm just watching this bit. So if that bit is a 0, I'm in one half of the space. If that bit is a 1, I'm on the other half of the space. And we'll see, like we'll spend some time on this looking at like seg faults, like what is a seg fault, what triggers it, and so on. This is what's happening in hardware. The memory manager watches these bits and it just makes sure that, oh, you're a process, there should be a 0 there. If there's a 1 there, you're trying to access something you're not supposed to be, and it's a seg fault. And because I'm only comparing one bit, like it's a really quick compare. All right, that's virtual and physical memory. This doesn't have a lot of utility for us right now because we really haven't talked about virtual memory, but basically it's a way to fit all of those 4 gig processes into a limited amount of physical memory. And we'll go into nauseating detail about that soon. You'll be sad you saw that. So that's our address space. What's in there is tons of stuff, like all the variables we define in our program, the actual instructions in our program, like the code that's going to run, that's got to go in here into memory. The structures themselves, like the heap and the stack that we keep talking about, I have to have space for those and so on. the way we store programs, like when you do a compile, I mean, basically what's happening when you compile is you're taking C, you're compiling it down to assembly language, then you're running the assembly language code through an assembler, and that creates binary instructions for the CPU. Like if I'm trying to add two numbers together in C, that's a certain set of Intel specific instructions for the CPU to move a couple of numbers around and add them together. So the C language is really an abstraction on top of assembly language. Assembly language is an abstraction on top of binary because really the CPU just wants to see ones and zeros. It's a binary machine. But all this has to be stored in a file system somewhere. And then we're going to read that file into memory to create a process. And now I can run the process. The format varies depending on what machine you're on. If you're on a Linux box, like in your containers, you're looking at ELFs. ELFs is this the executable and linkable format. On a Mac, it's a Mac object, a mock object. Mac OS is based on the mock kernel, which Steve Jobs borrowed for his next operating system. Mock came out of MIT. It's a Linux, a Unix-based sort of thing. They look like this. So this is looking at, if I took a file of your executable code, like you do compile my code, create an executable file that I can run. This is what's in that file. So there's a header on the very top. The header just tells me what kind of machine am I on? What's my word size and so on. In fact, we can see that. Can I get out of this? Bip, bip. So let's do like, where would I have an executable? User bin maybe. So let's pick something like, oh man. So man, what the file command, and file, self-referential, file. So file reads that header. It's basically reading that ELF header, and actually it's a mock header in this case. It's reading the mock header and telling me what this file is just by reading the information in that header. So here it said, what is it? It's a universal binary, a mock object. It has two architectures. So it's got an ARM architecture and the Intel architecture. So this file could run on an M1 as well as the Intel box. Should tell me what my word size is, 64-bit. So it tells you a lot of information. It then has a bunch of sections in it. And the sections are where our things go. So that text section, for example, the text section is our executable code. The code doesn't change, like it's going to be a fixed size. We compiled that down into something executable. It's a bunch of binary. Well, that's what goes into the text section. Read-only data, RO data, strings. Strings are immutable in C, so there's no reason to write it. Once I've defined it in my code and compiled it, that string is never going to change. So that goes into a section of memory that's read-only, RO data. The dot data section, that's stuff that I've initialized, like if I have global variables, we haven't really made a distinction about global variables or statics, but if I've initialized variables, they're going to go in this little section of the file, and so on. BSS is uninitialized stuff, so I've got space for it, but there's nothing in it. It's actually just a bunch of, it's just a header, kind of it's marking a space for those variables that I'm going to need later on. BSS stands, it was actually an IBM opcode break on switch or something. Better save space is how I remember it these days. Joyce says, I'm saying mock, not mock. Yes. M-A-C-H. The bottom half of this thing, mainly the bottom half is for debug information. So symbol tables, so if I'm doing debugs, I've compiled with the -G option out of GCC, for example, that saves symbol information. It's basically just mapping my variable names onto the symbols so I can go find them in memory by name. Show me node, where's node? Well, node's really a binary symbol somewhere, but if I did a -G when I compiled, it would save off this little table that mapped the name of the variable to its symbol, and I could go find it. Line numbers, debug information, and so on goes in this bottom section. I'm going to read this into memory. When I double click on something or say run it, like it reads this file in this format into memory and plops things into memory for me like this. So this is the process view. This is the process's view of its 4 gig memory space. Now, some really interesting stuff in here. Lasers. So here, for example, this is that split. And in these operating systems, these architectures, it's not a 50-50 split. I can't remember how far that goes. I think it's 0xC00 is where that goes. So it'd be the first 2 bits maybe that of memory address that is mapped over that break. But everything up here, this is the kernel stuff. And if our program tries to access that memory directly, it's a seg fault or a segment violation. Everything else down here either came from our file, from our executable file, or was built for us when we created this process. We'll go through the process creation steps at some point soon. And again, this, it's not an operating system course, but we're still interested in how is the process created, because like it's our process. We want to know what are its limitations, how does it fit in memory, and so on. So all the stuff from our file is down here in this little blue and yellow section. So there's my data, right? Here's my text section. Text is our executable code. RO data, that's our immutable stuff, strings and so on. Up here in the data section, data is for initialized globals. If I said int a equals 5, that's going to live in the data portion in this little purple section. And again, these are all just memory cells, right? 8-bit memory cells with values in them. And then there's a map. That symbol table lets me find, oh, where is A? Oh, it's in this location in memory. What's its value? Oh, it's a 5. So that's the bits that get read in from our ELF-based binary, ELF formatted binary, and then everything else is created at process creation time for us. Like this, for example, there's your heap. That's the runtime heap. Here's the stack. We're going to use the stack when we do function calls, not directly, but like that's the mechanism we use for function calls. This stuff in the middle, this user map stuff, we don't care about this yet. We're going to use that piece for when we do threads, start writing threaded code. That's going to be memory that's shared among threads. Well, the issues we have, like, remember I've said, like, actually somebody in A1 said, what's a Stack Overflow? It's this. So when you call a function, time is it anyway? I got tons of time. When you call a function, it's not like it's not contiguous. So when I call a function, I've actually got to jump to some location in memory, wherever that function happens to live, its first instruction. I got to jump there. It's really like a break in what I was doing. I'm going to go run the function and then get some value back from it and then keep going. Well, the mechanism that's used there is called a stack frame, S-T-A-C-K frame. That stack frame is created up here in the user stack. Didn't know it was loaded. So the stack frames are created here, and it has information like what parameters am I passing to the function? What parameters am I passing back from a function? What's the return address I need to go to? Like all sorts of information about the function call. That's a stack frame. And then I do the function call, and the function uses information from that frame. Let's say I had a runaway recursion. I forgot the base case in a recursion. So it's just going to keep calling its function over and over and over again. Well, every time it calls the function, it creates a new stack frame from here. If I don't return from any of those, like I just keep calling the function over and over, I keep building stack frames. Well, the stack grows from here, this direction. So it's growing from essentially the top of memory down. The heap, if I'm allocating stuff up the heap with mallocs or something, or reallocs or whatever, if I'm doing a bunch of mallocs, malloc, that memory is taken from here and it grows that direction. So there are like two cases or a combination of them. If I have a runaway recursion, or if I'm just calling functions over and over and over, I keep building up stack frames. The stack grows, it's eventually going to run into something, and the program's going to crash. That's a stack overflow. If I'm mallocing like crazy, just allocating tons and tons of memory or big chunks of memory, that heap grows this direction. It's eventually going to run into the stack, and the program's going to crash. So it's important to us to like manage these things to make sure that we're, from the process standpoint, our program is managing its memory cleanly. I don't want to have a bunch of dangling pointers, memory leaks. It's going to fill up this space pretty quickly if I've got that. If I'm doing a lot of recursion, I got to make sure I have all my base cases so that I don't run out of stack space and so on. Jonas says, why do we have an unused bit on the bottom? Well, notice where that unused bit is, down at 0. What do we map 0 to? Null, right? So if I've got a pointer pointing to address 0, null, and I try to access it, that's outside my space, and I'll generate a segment violation. So it's really used as kind of that's our guard for null pointers. I'm sure there's something else down there too, but that's what mainly we use it for. Yeah, it's just 0, 0, 0, 0, blah, 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 all the way down. That's a crash. At the heap. Oh, sweet. Sweet. Nice. This is cool stuff, right? Like this is, yeah, you're welcome. So this is what a running program looks like in memory. And there's a whole bunch of other stuff that goes around this, like how do I know what line of code I'm on? Well, that's something that the CPU keeps track of. It's called the program counter. The program counter is just the memory address of the next instruction to execute. It's a register, a physical register on the CPU. It's part of the process. This is just the process itself. There's also a process header that the operating system keeps, and the process header has information like what pieces of memory have been mapped to this process, so I know what segments I own. What's the program counter? What's the state of all of the CPU registers, at the moment that this thing is running? Because at some point this is going to be pulled out of the CPU, something else is going to run. So we need to maintain state. We need to know what all those registers had in them. What was the program counter and so on. So that's the operating system's bookkeeping for each running process. We're going to care because we need to know things like, oh, I might need to use the registers on the CPU. I can do that from C. I have direct access from C to the registers on the physical registers on the CPU. How would I do it? I would probably do it by embedding assembly code in my C program. And that's actually a pretty common technique, especially when I'm looking for performance, like a Fidelity, where I worked for a while, consulted for a while, on the trading side, stock trading. Most of the trading systems are written in C, except for the pieces that absolutely had to go as fast as possible. So those were written in C. In C, I can embed assembly language with a directive, almost like an include. I can say, hey, C compiler, this stuff in this little chunk, this is assembly language. I don't want you to do anything with this except assemble it when you get down to the assembly and linking process. So if I needed access to directly to registers, I can do it in C with embedded assembly code. So it's because C is so close to the metal, right? I can get to stuff directly in memory. It's really, really hard to do that in other languages. All right. So there's another slide or two, but this is where we stopped in A1. So I'm going to stop here also. On Thursday, what I want to do is we'll finish up on that slide or two. Basically, we're going to play around with object dump to just take a look at some stuff. On Thursday, I want to look specifically at the heap. Like, how is the heap built? How is it managed? When I do an allocation or a free, like, where does that memory come from? Where does it go? And so on. And then the following week, we'll start to look at things like virtual memory and that piece of memory operations. Actually, we'll look at the stack starting the following week. and we'll use the same sort of technique. Well, like we'll look at the stack this way, and then we'll go into C and like write some stack code so you can see actually how it works. All right, so that is it for today. 50 seconds. Whatever you want to do with those 50 seconds, they're all yours. I'm gonna leave, so good luck. All right, that's it, guys. I'll see you on Thursday. Don't forget to read Piazza for PS3 stuff. You're welcome. You're welcome. Always welcome. Love this stuff.